calculus of computation. In analogy, calculus of differential calculus of integrals. There are tools such as mathematical simulator that help a lot when you have, say, calculus, integral calculus models. Whereas for programs, I'm taking an example from an early paper by Alan Turing with foreshadows programming application. And what's illustrated in the flowchart is the factorial program, and he has annotated the points of the flowchart with assertions that are true for all executions that traverse the edge of the flowchart. So this data was really solidified by Ford with this flowchart annotations. So for those we have tools to now set3 has been was developed specifically for software, but it's also the interface to it is first order logic, and that turns out to be fairly generally applicable. So here's a set of tools and areas where it's been used over the years. Personally, I've been involved in the network verification space and also in the dynamics configuration space, where you can use it to calculate valid config states, for some smart contract space. But this basically is to illustrate that you can that it's fairly broadly applicable. And I see with some exotic applications in axiomatic economics. The technology that set3 is based on is borrows and steals and is inspired by related solver technologies. So if we classify the areas based on efficiency versus expressive power, it's well advertised that propositional stack solvers are extremely efficient with what they do, but their language is proposition logic, so you might have to write down a very large format to say the same thing that you can say in a more expressive language, such as first order logic. However, the technologies used in modern stack solvers has strongly influenced the main technologies used in SMT software, so conflict theory. Similar to mixed integer programming, is based on simplex and branch and bound form class, and those technologies are also important in SMT solvers for formulas involved arithmetic. Finally, constraint solvers, constraint satisfaction solvers, they revolve around the main workhouse or local propagators. And that is analogous to having theory solvers. So in SMT, we have a theory of arithmetic, a theory of arrays, and other data types. And for each of these theories, there's some engine that knows how to reason about such formulas. In constraint programming, we have a so-called theory of drop shot filling up a resource, constraint resource, and we have a theory of how much you can fill up with drops in the constraint resource. And this is just a joke about first order format. Whether they are slow or efficient. Okay, so back to the main.
Presentazione, Identified is back.
And they are organized.
Questa è buba.
The first 5 of these areas are organized through the influences that initiated their development and then their impact. So let's dive into symbolic model shaping. So symbolic model shaping first was started in the early 2000s in Microsoft as a standard. by a binary relation and between the input and the output. So what you have in the first argument is the input, the second is the output. So what the first clause will say is that if the input is greater than 100, the output is the input minus 10. And the second line will say that if the input is less than equal to 100, then first I'll add 11 to the input, get it into the result, and compute make another recursive call to the function, and that's the result. So that's the bit of the workload you see here. And then the last line talks about a specification. It will say, if you run the system from X to R, and when X is less than 101, the result R is 91. So that was the specification. So what the tool does is it tries to check whether this set of causes are solvable. And indeed, there's a solution for AC such that each of these lines is true. And that will guarantee that the specification will be told us. Question? If you have questions, go ahead. But otherwise, I'll charge ahead as quickly as I can, because I'm running out of time by the end, or happy to keep you in this room forever. Okay, so that was symbolic, an overview of symbolic model taking. So let's go to model-based testing and model programs. So in the late 90s, a group was formed in Microsoft Research around abstract state machines. And the goal of that group was to develop tools for architects of systems. So the idea was that we write down architect a distributed system as an abstract state machine, and then they developed tools for it. It turned out to be picked up mostly by testers, and then for protocol validation. So the spec export systems are used for compliance of protocol documentation. So Microsoft will produce documents of all their protocols. So for example, I developed a distributed file replication system between 2002 and 2006, shipped, and then I had to document this replication system in a way that independent vendors could write their own implementations of it. And then the spec export tool was used for validating that, to cross-validate Microsoft implementations with the independent vendors. But so that faded away. But new tools keep popping up, and so one I will talk about on the next slide is Zen tool that falls in this model-based world. So Zen is embedded in C# and uses link, so reflection, so you can write down expressions as programs, and those expressions can be reinterpreted as logical formats. So here's an example of an interpreter for firewalls. So the interpreter takes a network security group, a packet, and the index of the current rule. So the rules are in the network security group. So if you traverse all the rules, then the packet is not allowed. Otherwise, you process the current rule. And if the packet matches the current rule, then the packet is permitted. Just assume that all these rules will permit the packet. Otherwise, the packet is allowed if one rule in the tail applies. So the point is that once you have a set of rules, you can execute this program, unfold it into one formula, and then calculate properties of this program. And so it can be used for test case simulation, for example. And towards the end of the talk, I actually have another use of Zen. Now, systems code verification. There's essentially two camps around it. One from the functional programming world, developing programming proof obligation. So the developer of UPB is a colorful personality, so I have this as the happy face, whereas the functional programming world have all these complicated typing rules. So you have the contrast here. So I'll talk about if star here. So if star is a typed functional language with defining types, and it uses a tree as a backend to discharge verification conditions. It can also compile to a panel, and where they're sending C, and if you're targeting C in particular, it contains a sublanguage that we call low star, where when the code looks like C, but has semantics in terms of their star, but then as since it looks like C, also there's a corresponding compiler to C or where it's sent. Veil serves the purpose of when you have a semicolon and want to verify the semicolon, and simply it reflects into a semicolon. Then there are other domain-specific languages for concurrency, backends for Rust, sub-languages of the domain-specific language of C, specialized parsers, network parsers, and then a host of other ways of you can interface with this framework. So this gives you an idea that you have a way of generating code to target architectures, whether it's C or Rust. So these days there's a high interest in generating Rust code, but not everything is possible to run Rust, so you may also retarget to C at the same time. So the same front end you can use for different backends. So Enterprise is quite a bit of has been quite a bit of success. So it's been used in the hypervisor virtual switch since 2019, and replaced about 30% of the code is now fully verified network parsers. So it used to be the case that 20% of a good fraction of the bugs that have been exposed in the hypervisor were due to faulty parsers. And so the whole class of bugs that are now absent thanks to this toolchain. And what it looks like is that you give the packet format, and it looks like a C struct, but you also have type annotations. So you can annotate the fields by constraints on the values, the legal values that you have. For example, the min and max field must be sorted. So the min must be less than equal to max for the packet to be well formed. And then given these well formed constraints, you can synthesize a correct parcel that doesn't crash, doesn't need uninitialized. And this.
How do you know the checksum?
What?
Yeah, I see the checksum. How do you know that?
I haven't modeled myself, but I'm not sure if you need to model them.
Is there a big part of the validation checks for packets?
So is the validation check for whether the bits are true. I should say it's a second. It's a validating that for bit corruption.
Basically, so before you do anything, you check that, and then if that aspect of the check, then you need to go and get the validating implementation.
Right. So you're asking, so what is it that we verified on CRC?
It's the implementation.
The implementation is CRC.
Yeah. Is that using trusted or?
I believe it's also verified. Definitely, what I can say for
easier to target LLVM IR, and then everything that can translate from front end to LLVM IR basically support every language.
So what in Rust, so I don't have an example of using Rust on the slide, but essentially you add the language you are going to write assertions, the looping brackets. So that's before you, so it's not convenient to write your assertions at the LLVM IR. So the idea is we develop a program and improve it on the developers. So this also has a user angle here. When I talked about the symbolic model shaping, the assumption was that this is automatic. So these are tools for automatically improving safety policies. They're weaker, you can prove everything that they prove in these frameworks. But in that case, we really learn you asked specifically of IR.
On IR, you were talking about LLVM integration, if I saw correctly. So this is why I mentioned LLVM IR.
Okay. So maybe there's a minute to my answer, which is that, okay, so there are some new activities about exploring LLVM IR.
Okay.
But still, I think the answer is that if you're specifically writing Rust programs, you want a methodology that maps to Rust. And that's the main thesis here of introducing yours. It's also used recently two papers at OSDI, winning best paper awards. So it's getting picked up in other institutions. So now I want to talk about a very different area that I will characterize as the tomography of computation. And the idea is that we observe executions and behaviors of programs as they run, and then we make inferences about properties of those programs. So specifically, when we test for concurrency, two approaches that were developed at Bell Labs in the 90s, in the late 90s. Very soft is a stateless model, so it can spin as a stateful model, so it can protocols. And they inspired two threads of tools in Microsoft. One was chess, where chess will control the scheduler, and the insights underlying chess became distinguished from Versa was an insight that you should only need a bounded number of context switches to explore all of the relevant box scenarios. So if you have a recursive block, the thesis is that it's going to happen after a bounded number of context switches. So you restrict the number of scheduler changes, and that drastically reduces the search space. And now, just with deterministically change traverse context scheduler changes, but then the realization was that if you use probabilistic methods, you can get probabilistic guarantees about coverage. So the class tools was introduced, and that's part of the amplifier. So it can be used for fuzzing kernel level comparison blocks since 2008 or so. Now, the modern tools that are also used in this inside out context switch and probabilistic schedules are called Torch and Coyote. So first of all, just recap what I understand by this bounded control concurrency system. So if you have a system that, depending on what thread is running and exhibit different behavior, the So the two current big tools these days, so Toyota is a design level tool, and you write, as you're writing your C# or now C++ application, you use a library that is enabled by the Toyota. The Toyota evolved itself by first requiring specialized library you'll see something about that if you receive a packet from one place to another, you will either bounce down from tier 2, you will bounce down to tier 1, top track, or you will go to tier 3 if there's no direct path. And so we take these rules, and then together with the topology information, we can make a global guarantee about the full network. So we put the configurations and then check it a few times a day for all hours of that stuff. So there's a few 100,000 hours of each hour a day, 10,000 pieces. So the takeaway is that we're essentially inspired by the I guarantee reasoning that we know from program application, and then using it in this network space. I think the network change verification system is an end-to-end system for when we deploy repaid regions, is what it's called. It works in the following way that we take the policies, network policies, then you simulate them using the network convention software that was worked on years ago when Microsoft. And then that tool generates a forwarding plane. On top of the forwarding plane, we can take reachability and policy questions using a tool used here called SPOT. It's used on a regular basis because the networks that we make periodically. And so basically the baseline is that we've historically seen without such a tool with observed values. A newest tool in deployment is based on SED that I used earlier. And here it's used for network experience of virtual networks. So customers have their network requirements in the cloud and they want to ask, can we get from A to B? So here the reachability tool uses binary precision diagrams to encode the forwarding table, binary precision diagram transfer function, and then it does reachability checking of the binary precision diagrams. And that was deployed earlier this year. And I think we had an early alpha tester from Bulgarists years ago. So now to the AI. So here the claim is building AI software is going to introduce new kinds of questions. So today Microsoft is developing, others are developing software based on foundation models. And it gets integrated in Copilot and Bing and other Copilots. The way it looks like that are no